Hi again. This was a review session for Module 1 and things that we have covered in Module 1. I hope the last example that we did, which was regarding the thrust that a blade in a helicopter, a rotating blade in a helicopter will feel or experience, has convinced you that usually the complexity of the flow and dynamics for these problems is not really easy to handle. But what we can do and what we have learned in Module 1 is the fact that by use of simple physical principles, we can draw certain boxes around our problem, isolate it from the outside or external world, and talk about forces from the external or outside world, such as the weight of the helicopter and the balance of momentum coming in and out of the system, and connect them together to find relationships that really tell us how, for example, the weight of this helicopter is balanced by the change of linear momentum that is happening in the vertical direction as fluid elements with almost negligible or zero velocity come into the blade from the top side and then exit the blade from the lower side with a certain considerable value of velocity. I really encourage you to think about these concepts before the final exam, but also I'd like you to tell you what are the limits that we didn't have time to cover in Module 1, and hopefully you will like to hear about them in Module 2. As you can see from this image, there is quite a bit of vorticity and vortex-like motion around the tip of the blade that we really don't talk about it in the contour volume approach. Those are all the things that are inside the black box of a contour volume, and we really don't address them. However, if you like to understand those complexities, the nature of those phenomena, and what are the underlying principles and equations of motion for those specific details, I encourage you to think about Module 2. In Module 1, we did not really worry about them because we used what is called as integral equations. In other words, we took the governing equations but looked at them when we apply them on a big volume and when we integrate those equations to big volumes. But if we go to a differential element, we can actually think about those differential equations, or differential equations of motion, I should call, and think about different effects and different phenomena that will be happening as a consequence of those governing equations. For example, let's look at what will be a set of different problems that Module 2 will address and we will cover in that module. On the right, you will see a picture of a stream of honey falling down on a bread. We definitely know that viscous stresses are extremely important and significant in that phenomena. We really didn't talk about viscous stresses that much in Module 1. Most of the flows we studied were inviscid. In Module 2, we will go into the details of those viscous stresses, how we can capture them, where or when we can say they are dominant, or when or where we can say they are not important. And it's all captured through this very important governing equation known as Navier-Stokes equation, written at the center of this slide, that will tell us how these different terms will interact with each other. What you can clearly see, this equation of motion, which we call Navier-Stokes equation, is very similar to Euler equation, with one difference, that an external term, an additional term, which is a viscous term, is introduced. The term in red, which is viscosity times Laplacian of the velocity, is capturing the entire effect of shear viscous stresses acting on fluid elements. In Module 2, we will go into the details of this equation, Navier-Stokes equation. We will show you examples very simple enough that we can solve it. And we will definitely tell you how, by proper dimensional analysis, we can compare the order or the scale of different terms with each other and decide in what regions or in what ranges we can ignore certain terms and in what other ranges we cannot ignore them. Proper dimensionless number that will emerge is the Reynolds number that we will introduce in Module 2, and based on the Reynolds number we can separate the flows to very viscous, like the honey example on the right, or relatively not viscous or inviscid, like the vortex flow behind the wing in the example on the left. These are all exciting examples, and I hope you guys will follow Module 2 with us and learn from Module 2 and the concepts covered in Module 2 new ideas and new thoughts that can help you to understand and solve different problems that may involve a little bit more of differential approach to fluid mechanics problems. It definitely involves more mathematical concepts, but I will guarantee to you that it will be rewarding for your understanding of this interesting concept. With that, I thank you for listening to the review session of Module 1, and I hope that you will be with us in Module 2.